All right, hello again. Welcome back to some more of me standing here talking about physics. Yeah. So this is the last part of the course, and it's going to encompass light. We're going to talk about light for a little while, and then we'll get in. That will sort of lead us towards what you might call modern physics, or get into the more kind of contemporary areas of physics, or more recently discovered areas of physics, and those being stuff like nuclear physics, quantum physics, general relativity, yeah, some cool stuff like that. So we're going to start out, though, as I said, talking about light. Okay? So this whole lecture is going to be about light. The next lecture is going to actually be more stuff about light. And then the lecture after that is going to be probably just even more stuff about light, and then kind of leading us towards nuclear and quantum physics. So why so much talk about light? Well, light's a very special thing. If we didn't have light, well, you wouldn't see anything. You wouldn't see me, for one thing. We could hear each other, but our experience of the world would be much different. And on another level, light has come up in a number of ways beforehand in this course. First, maybe when we were talking about types of heat transfer, one of those types was radiative heat. And in explaining that, I told you that's basically, literally is, a form of light, infrared light, that can transfer heat up objects. So that's one way that light's kind of a special thing. Infrared light transfers heat, pretty useful. Visible light, the way we're seeing, you're seeing me, you're seeing this, you're seeing the TV screen, or whatever screen you're watching this on, you see anything. Right? Your eyes work with visible light, and we're going to talk about those in much more detail. And then also, when I first talked about light, I believe give you a little bit more of a broader idea that there are things well beyond just visible light and infrared light, and maybe we talk about ultraviolet light, but there's also things like microwaves and gamma rays and X-rays, these things well beyond or very far away from visible light in our spectrum, or in the electromagnetic spectrum, but still they're all light. They're all electromagnetic waves. So the end of the last section was electricity, magnetism, and kind of coming to the realization that those two, electricity and magnetism, are both part of the same thing, namely electromagnetism. And those two things create, well, there's electromagnetic fields, and it turns out that waves in those fields are light in the most basic sense. Okay, so enough with that. Let's keep going. Right. So, electromagnetic waves. Right? So light is another term, and light gets thrown around in different ways. The term light. Electromagnetic wave is the very broad, encompassing term for a wave in the electromagnetic field. There's electromagnetic fields everywhere. So those electric and magnetic fields are generated by electrical charge. And remember, if you have stationary charges, they'll generate electric fields in various different ways, or different kind of topologies or forms. The way will look different depending on how a charge is arranged. But if you have that charge in motion in some way, then you generate magnetic fields as well. It turns out that the electromagnetic field is something that just exists everywhere. It turns out that throughout all of space-time, there's this electromagnetic field. And when that field, you think about it as like the surface of a pond, So throughout that surface of the pond, there's water on the, that's the surface, is water, but there can also be waves on that surface. So when you have oscillations or you have things vibrating on that surface, then you start to generate waves. So in a similar way, there's electromagnetic fields all around us, and the movement of electrical charge will generate waves in those fields. So we get electromagnetic waves, and those electromagnetic waves are different forms of light. So as pointed out here, the electromagnetic wave that we're most familiar with, is what we call visible light. Right? So I'll try to distinguish when I'm talking about light in general versus visible light, meaning like the light we see from the sun, from lamps, and things like that, fires. So remember that all waves have some fundamental properties like the wavelength, frequency, wave speed. Remember those from our last section, hopefully. It turns out that visible light is an electromagnetic wave within a certain wavelength, and it turns out that's about 400 nanometers to about 700 nanometers. In terms of inches, it's somewhere about a couple hundred thousandths of an inch. So you take an inch, you cut it up to 100,000 pieces. It's like one or two of those, somewhere around there. So very, very small, right? Incredibly small. And as shown in here, we're going to get talking more about the electromagnetic spectrum overall. So like the full breadth of possible wavelengths that light can come in. So light in general is just electromagnetic waves. You can see that this chart sort of shows the full spectrum from very, very short wavelengths all the way to the left, moving over to very, very long wavelengths all the way to the right. So somewhere, not necessarily in the middle-ish, the spectrum is very, very broad, but inside that spectrum is where our visible light lies. Right? So visible light, right in the middle there. And you go very, very short wavelengths, you get to something like 10 to the -3 nanometers, even shorter than that. So you go, visible light is already a very short wavelength, but it turns out that the electromagnetic spectrum goes even further beyond that to go to very, very short wavelengths. And that turns out to be X-rays and gamma rays. And then on the other side of visible light, we have the longer wavelengths that are longer than visible light, which would be like microwaves and radio waves. But the visible spectrum is actually just this small kind of chunk in there. And that's all the stuff that we see. Okay, so, right, we're talking about waves, electromagnetic waves in this case, and the thing that's waving, that's the material, is the electromagnetic field, and that's all around us, it's everywhere. It turns out that electromagnetic waves are transverse waves, as opposed to longitudinal waves. So being transverse waves, the amplitude of the wave, or the thing that moves, the material that's moving the field, is moving perpendicular to the direction the wave is traveling. So if the electric and magnetic fields are moving, say, up and down and left and right, like this, then the wave itself is propagating straight away from you. So in a sense, being transverse waves, they can sort of think about it as being like water waves, right? Water waves are transverse waves. The water is moving up and down as the wave propagates along the surface. But it's more complicated than water waves, so that's a start. It's three-dimensional instead of just sort of being on like confined to almost a two-dimensional surface of the water. Electromagnetic waves inhabit 3 dimensions, and in order to sort of transition to thinking about water waves, from water waves to like electromagnetic waves, you have to think about not just watching ripples go on the water, but somehow there's another movement that goes horizontally at the same time. So it's a little bit tricky to imagine. But let's just check out what a water wave might look like. Oh, sorry. So before that, well, actually, let's just. So here, this is just a simulation of a water wave, but you get the idea where there's sort of this constant perturbation, or this like maybe just thinking about constantly dropping something in the middle of that picture. So if you were to disturb the water right in the middle of this image, then you'd make these ripples, right? They're coming out. You push down on the water, then it comes back up. Push down on the water again, it comes back up, and so we create these ripples in the water, and the water itself is just moving up and down, but the ripples are going away. Okay? So in the same way, when you have an electric charge, so instead of like your finger causing the ripples here, if you have an electric charge like an electron, and it's moving, you're moving it up and down, you're sort of in the same way you're causing ripples in the electromagnetic field. So this picture we could think of as maybe the electric field part of it, and then the, like again, to imagine that there's sort of a sideways motion that's possible too, or a horizontal motion that's possible beyond just the up and down the ripples. There's a left and right thing, and that's sort of like the magnetic field. So this is kind of a picture you could also think about as a electromagnetic wave, but there's got to be this like hard to imagine sort of horizontal motion going on as well. All right, so in order to try to imagine that a little bit more, you can make these images of electromagnetic fields, or waves, sorry, being the waves being ripples in the electromagnetic field. And what we can, well, this just gives you a bit of a visualization where the electromagnetic wave is propagating sort of left to right here, and the way that it propagates is by increasing and decreasing the amplitude in the electric field, and then also increasing and decreasing the amplitude in the magnetic field, but the electric and the magnetic field are perpendicular to each other. So that's what I was saying, like there's like the ripples like the electromagnetic field, or the electric field, but there's this horizontal motion going on at the same time as like the magnetic field. So in order to generate this, maybe at the very far left, you can imagine somebody's grabbing an electron and just kind of jiggling it up and down. And that would generate this electromagnetic wave. And should also say that this is a simple electromagnetic wave. This is sort of the simplest kind of wave. It's called a plane wave. There's more complicated looking versions of this, but this is sort of the basic type of wave. And you can actually think about other waves as being constructed of multiple ones of these, or overlapping waves like this. So there you go. Okay. So recalling that also besides having a wavelength and this amplitude, waves have a wave speed, and light's no different. I've talked about the speed of light before when we were comparing it to the speed of sound, mostly by saying it's much, much faster than the speed of sound. The speed of light is incredibly fast. It's the fastest thing in the universe, it turns out. It sort of sets the universal speed limit in a way. And to be a little bit more exact, the speed of light, we would say in a vacuum. So when there's an electromagnetic wave propagating and there's nothing else there, there's no gas, there's no solid, there's no liquid, there's no plasma, there's nothing else in that space, light, or the electromagnetic wave, will propagate at its maximum speed. And that maximum speed is about 300 million meters per second. Yeah, incredibly fast, unbelievably fast. So, so that's the maximum sort of speed. And in other materials, it actually goes a little bit slower. And in some materials, it goes quite a bit slower, but even half of the speed of light in a vacuum is still 150 million meters per second, which is still crazy fast. So saying light goes slower in materials doesn't mean it goes slow. It just means it goes relatively, it's a little bit slower. It's still incredibly fast. But yeah, so if we know light has this speed, then Well, we can think about what the wavelength of some different electromagnetic waves are. So for instance, if you're listening to a radio station, if you're listening to it in your car or something like that, you're listening to an FM radio, then you might be listening to a station that's around broadcasting at around 100 megahertz. So like 105.3, that's 105.3 megahertz that they're broadcasting at. So you calculate the wavelength of that wave, of that electromagnetic wave that's broadcasting the signal, that's carrying the signal. The wavelength would be its speed, so we'll just assume that in air it's still about the same speed as it would be in a vacuum, so 300 million meters per second divided by the frequency, 100 megahertz, and mega is short for million, so 100 million hertz. Turns out that the wavelength of that station's broadcast is about 3 meters. 3 meters, about 9 feet. So, it's pretty long. It's bigger than you. So it's just an idea of the wavelength size of other things, right? Visible light, the light that we see, very, 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 very short wavelengths. Radio waves, pretty long wavelengths, right? You can go even longer wavelengths too. Some other examples might be infrared light, say at 300 gigahertz. Right? There's a whole spectrum of variety of range of infrared, but 300 gigahertz is in there somewhere. And if you plug that into this equation, it tells you that the wavelength of that light is about 1 millimeter. And visible light, another example, the frequency of one type of visible light, or one kind of spot in the visible spectrum, is maybe 515 terahertz. So giga means billion, so 300 billion hertz. Terahertz is a trillion, so 515 trillion hertz. Turns out that wavelength is about 580 nanometers. So like I told you, our visible spectrum is between about 400 and 700 nanometers, right? So this visible light would be 580 nanometers, and that's basically yellow light. All right, so then moving from that longest wavelength part of the spectrum to radio waves. And and radio waves, like we calculated the FM wavelength, that FM wavelength, the 100 megahertz, was about 3 meters wavelength. But radio waves can be even longer than that. They just go out longer and longer and longer. And, they could be up to the scale of like buildings, even longer than that. So that's the longest wavelength, the lowest frequency end, and very long, very large wavelengths. Then we move into the next shorter wavelengths, would be microwaves. Again, named very aptly. Microwaves, like microwave ovens, they use microwaves, so that's where you encounter microwaves very often. And the scale of that is, the size of the wavelength is like the scale of a baseball, right? Normal size sort of objects. And moving from slightly higher frequencies from radio waves. Then we move into infrared, the infrared part of the spectrum. Again, getting shorter wavelengths, so we move to the right here. And infrared we might use with TV remotes. The scale of those waves is sort of like a pin, right? Or a pinhead even. Right, and then we're getting into even shorter wavelengths. Now this is our visible spectrum, right? All of the color that we see is all light within this wavelength, or this range of wavelengths. And those wavelengths, the scale is sort of like a bacteria size, right? Like we said earlier, that 400 to 700 nanometer-ish. And visible light. So then we keep going shorter wavelength. On the other end of the visible spectrum is ultraviolet light. And you get a lot of ultraviolet light from the sun. Black lights emit ultraviolet light. And the scale of that is even smaller than bacteria, so now we're on sort of virus scale. So these are just examples to give you an example of the scale. Keep going shorter, we get into sort of the X-ray area. And yeah, so these are X-rays are used in X-ray machines. They're called X-ray machines because they use X-rays. Even shorter wavelengths. The wavelength size is roughly on the size order of like the size of atoms now. Again, it's a pretty broad part. Like, there's a large range of wavelengths here. So the atom is sort of in there as an example of that sort of size. And again, as we go to shorter and shorter wavelengths, we're going to higher and higher frequencies. And then finally, on the far end of the spectrum, the shortest wavelengths in the electromagnetic spectrum are gamma rays. And gamma rays you would get from radioactive materials, nuclear decays, things like that. Size then being essentially on the order of the smallest sort of stuff, these subatomic particles, the size of an electron or a proton or a quarks. And those are the highest frequency wavelengths. It also turns out, I don't know if I mentioned this before, but the frequency of an electromagnetic wave is essentially proportional to the energy that wave is carrying. So gamma rays are the most energetic of waves, and radio waves would be then the least energetic. Okay, so hopefully pretty straightforward question then to ask yourself. So which of these examples is fundamentally different from the others? So hopefully I know the answer already, but maybe take a second, pause it, and think about it. Okay, so hopefully you answered sound waves. You can think about that in a number of ways, but the main thing is light waves, meaning probably visible, mostly talking about visible light. Radio waves, X-rays, those are all electromagnetic waves. All of them we just talked about. Sound waves, completely different. Not an electromagnetic wave. Sound was a longitudinal wave for one thing, whereas electromagnetic waves are transverse waves. Sound wave is a mechanical wave. There's actually physical things with mass that are moving around. But basically, light, radio, X-ray, all those are examples of parts of the electromagnetic spectrum. Okay, so let's just talk about some things that happen with light, right? So light will interact with materials in different ways. You can sort of mainly classify materials as maybe being transparent or opaque. And transparent meaning that light will propagate through it. So transparent materials being like glass or I don't know, clear plastics. Anything that's clear, basically, it's transparent. You can see through it. That means if you can see through it, that means that some light is probably able to propagate through it. So opaque materials are materials that will absorb light, and where the material itself, or the atoms or the molecules made of the material, actually absorb that light and either hold on to it or reflect it back out, re-emit it back out. So, for instance, a black tabletop is opaque and it doesn't reflect, like in general, usually for the most part, it doesn't reflect. Right? So you look at a black tabletop, you're only seeing some very diffuse sort of deflection of light. And if you have a material that absorbs but strongly reflects, that would be something like a mirror, or like this hubcap here, right? Where the light is not going through the material, it's actually being absorbed briefly and then re-emitted back at you. And then just to emphasize that whether a material is transparent or opaque is different, will be different for different kinds of light. So a material like glass is actually transparent to visible light. That's why we can see through glass, that all those colors, all those visible things come through. But it's opaque to ultraviolet light and to infrared light. As an example. All right, so then just some interesting thing about ultraviolet light in particular. So remember, ultraviolet light is the light where the wavelength is just a little bit shorter than visible light, or just kind of outside the visible spectrum. And if you have things like ultraviolet paint, UV paint, it's made out of material that's meant to absorb that visible or that ultraviolet light, and instead of sort of re-emitting that same kind of light back, it re-emits light at a lower wavelength, a longer wavelength, sorry. So if you take ultraviolet light and you spread the wavelength out a little bit, you get back into the visible spectrum. So with ultraviolet paint, you have paint that will absorb the ultraviolet light that you can't see and re-emit it as visible light that you do see. So you get things like these sort of neon glow-looking stuff. And it turns out other materials will absorb ultraviolet light, and then instead of reflecting or re-emitting the same ultraviolet light, it will absorb it and sort of take in some of the energy and re-emit at a longer wavelength, so it's visible again. So that's why things like white colors, white clothes, will glow in ultraviolet light. So if you have like black lights, then you probably notice that bright colors will glow because they're absorbing ultraviolet light and re-emitting light, re-emitting that at a longer wavelength than visible spectrum. Another interesting thing, or an example of being opaque and transparent, is that UV light, like you showed in the last one, glass is basically opaque to UV light, so UV light's not going to go through. But quartz is another material that you can get make transparent, sort of looks like glass sort of thing, but it's actually quartz, it's not glass. And quartz, it turns out, is transparent to UV light. So let's check out what that means. So this is a rock, willemite, and it turns out willemite has some UV reflecting, or things that absorb and re-emit. Right, so the material itself has some parts of it that will absorb ultraviolet light and then re-emit that light at a longer wavelength, right? So that gets back into the visible. So when you shine a black light on this thing, the parts that are glowing green are the ones that are absorbing that ultraviolet light and then re-emitting it as visible light. So what happens essentially when he's going to take these little plate glasses is when he takes the glass and puts it in front of it, then the glass is going to stop that ultraviolet light from going to the rock, and so you don't see any of that glow coming back now, right? Because the UV light's not reaching that rock. Versus the second time he takes the little glass, what looks like glass, is actually quartz, puts it in front of it, it's transparent to UV light. So the UV light will go straight through it, will be absorbed, re-emitted, and that visible light will come back out. So there you go, the glass, can't see anything. And it might be hard to see, but there's actually a piece of quartz glass in front of it. Right. So I recommend, that might have been hard to see on the video, I'd recommend hitting the link down there and you can actually see it a lot better if you watch it yourself. Okay, so some other things that light does. Light, as you probably know, will cast shadows. Right? So when we think about light, it's a very interesting thing because you can think about it a lot of different ways. One way is imagining light as being like a ray or like a beam. So that's like, if you imagine light as just being like laser light in general. It just goes in like this straight sort of line. or light out of a nicely confined flashlight. You get a very nice beam, right? So sometimes we think about light as being a ray, and we can imagine it as like just like an arrow, almost like a vector, like you talked about before, but without magnitude necessarily, just the direction. And when we do that, it can be very useful because you can sort of analyze the effects that light has, for instance, when casting shadows. So essentially, if you have an opaque object and you put it in front of some light, then it's going to, in general, cast a shadow. So like this orange, it's casting a shadow. And the kind of shadow they cast, whether it's a very sharp edge, right, a very clear, distinct shadow, or kind of a fuzzy shadow, depends on a couple of things, right? It depends on whether the light source that's being blocked by that object, like this orange, whether it's a very large light source and very far away, so like the sun, or if it's a small light source but it's very close, like you have like a desk lamp. If you have a large light source, but it's very close to an object, so not just a desk lamp, but like imagine like a floodlight, and you bring an orange up close to it, you're not going to really see much of a shadow at all. Okay? So these are different things that affect how sharp or fuzzy the shadow is from an object. And we'll see, imagining with rays of light, why that is the case. So here's a couple of pictures, or two pictures, where we imagine a light source that's illuminating an object, or a light source here illuminating an object, and we're imagining what the shadow looks like on the wall around that object, behind that object. So if you imagine this light source, right, in the first case, you have the light source that's very, it's not a very large light source, and it's close up to the object. And all these arrows that are drawn are imagining just, this light source, it could be pretty big, and there's light rays that are leaving all points of the light source. So to get an idea of what the shadow is going to be like, you just imagine the light that leaves, say, like the very top of the light source, the light that leaves the very middle of the light source, and the light that leaves the very bottom of the light source. So the red, the green, and the blue arrows here. And if we draw rays, right, remember drawing light as just being like these light rays come off from the light source. Draw rays from the top, then we see that the rays from the top are going to go, or just sort of like the extreme positions that these light rays will go, are going to be right around the top of that object and hit just behind, right, just behind the object right here. But if that light ray from the top goes along the bottom of the object, it's actually going to hit pretty far out away from the object. Then we can imagine the light from the center of the light source. That light will go out past the object and hit on the top. It'll hit a little bit further up than the light from the top of the object, or light from the top of the light source. On the bottom, it's going to hit a little bit further in than the light from the top of the light source there. Finally, if you think about the light from the bottom, that light, when it goes along the top of the object, the closest it's going to get, it's going to hit a ways away from the object, right? Not really close to where that top light, right? And then the light from the bottom that goes along the bottom of the object, it's very close to the bottom, right? So very close into the object. So what we get with this picture is the two sort of parts of a shadow. The shadow in general is cut up into what you call the umbra, which is the darkest, the deepest part of the shadow, and the penumbra, which is sort of the fuzzy, lighter part of the shadow. So in the umbra, all of the rays that we've drawn from the three different points in the light source, none of them get through the object, right? So that's where our darkest part of the shadow is going to be. That's the umbra. Versus around the edge of the object, we find that there's this region where some of the light hits from the bottom, say, but not all of it, and some of it hits from the top. Some of it's in the middle, but not all of it. So we get this sort of section that's the penumbra. And the same sort of thing happens on the bottom. Right? So either the side here, we get this region that's not quite so dark because you have some of the light from the light source getting into that area. Okay, so here, when the light source is pretty small and it's pretty close, we get a fairly wide penumbra, a fairly fuzzy, imagine it's a fuzzy shadow. Versus if you take that light source and you pull it further away, we draw all those same arrows. Now it turns out that the light from the top that's going along the bottom is going to hit a bit closer in than it did in this case, right? And the light from the bottom that's going along the top of the object is also going to hit a little bit closer in. So what that means is the penumbra is kind of squeezed down a bit. So that fuzzy part of the shadow gets squeezed in, meaning that you're going to have a sharper shadow. You're going to have a smaller umbra and a larger, a more prominent, deeper part of the shadow. And if you just kind of take that extreme, push the light source all the way away, if it's very, very far away, you're not going to have that fuzzy part at all. All of the light rays are just going to hit into that object, and you just get that sharp shadow. All right, so let's just talk about some more stuff about light. So light casts shadows, and that happens to influence our perception in terms of distance, how far we perceive things to be away. And well, shadows sort of influence two kind of areas here, but there's a number of different ways that we sort of perceive distance given how light comes to us and the fact that it sort of comes as rays to us. So occlusion, meaning basically if you have objects behind other objects, then the ones that are covered by the front objects seem like they're further behind, or they're further away. Right? So there's a perception of distance there. And that in a sense has to do with the shadows, because the light that's coming from that object behind is not passing through the object in front of it. The object's opaque, doesn't pass through, and essentially that object's casting a shadow. The one that's in front of it is casting a shadow. So you don't actually see the light from here, from the second object, and we perceive that as being this object is behind it. Also, we have this geometric perspective, which we'll talk more about in a minute, but it's essentially the fact that if you take an object and you move it further away from you, even though it's the same size, we perceive it is smaller when it gets further away. So you take a 10-foot pole, and right next to you, well, it looks like 10 feet, but you move it 100 yards away, it doesn't look so big anymore. There's other stuff like atmospheric perspective, which is basically just when objects get very far away, the fact that there's all this air in between you and the object, you start to perceive this little bit of hazy bluish sort of color generally. And then specifically with lighting and shadows, you can perceive sort of depth with the lights and shadows, and whether or not shadows cast in one direction, maybe. So from the sun, there's a shadow cast in one direction on an object that's close to you, but there's a shadow cast in another sort of direction that's very far from you. Stereopsis, I'm not sure how you say that, stereopsis. But essentially that's the fact that we receive, the light that we see actually comes into two eyes, it comes into two different receptors for most people. And so the fact that we have a slightly different view, if I look at the camera, if you look at an object, you're actually getting a slightly different view in your right eye than you are in your left eye. And together, those things can combine, well, your brain is designed or evolved to take that information and be able to put together some kind of depth understanding or sense from the difference in those two. And then finally, there's relative motion. So if you have a nearby object and versus like a far away object, if you start to move, you move around a bit, then the nearby object, from your perspective, seems to move a lot more in your vision than the far away one. Because relatively speaking, you only moved a little bit in comparison to the far away object, but you moved a lot more in comparison to the near object. So all these different sort of things influence how we perceive distance, and they all are, well, the fact that we perceive anything by sight at all has to do with light, how light comes to us. So these all have to do with our perception due to light. So let's look at maybe a couple of these a little closer. Or sorry, maybe we'll take this as an example where you kind of combine a number of these things together. Right? So in early paintings, or paintings before, say essentially before sort of Renaissance time, when this idea of perspective became, and realism became a lot more prominent, sort of the norm, you would have images like the one on the left where there is some understanding of depth and being able to convey distance a little bit, mostly by the fact that there's occlusion, right? There's objects that are one in front of the other. And so just from the fact that the people in the front of the frame are covering the people behind them, you can understand that those people are further away from you. There's also a little bit, some bit of that geometric perspective of how objects change as they move away from you in the castle there. But most of in this image, it's sort of just that kind of occlusion, that objects covering objects, so you get the feel that they're further away or behind the other object. However, when you move into this Renaissance area, we start to utilize, or they started to utilize a number of these other properties or ways of perceiving distance. So in this Renaissance era picture, we have, well, a number of these different ones. Well, you have occlusion still first, like the people here, there are people obviously in front and behind each other. But you also have things like geometric perspective, right? So the people that are further away are much smaller in the image. And beyond just the geometric thing, we also have the fact that as you look at lines that are straight, even though lines that are parallel, from your perspective, if you looked at two parallel lines, they actually tend to recede and move towards each other, right? So you get some of that look in the lines on the floor here. You also even have this atmospheric sort of perspective. You can see that sort of like haze in the background. So you notice that the hills, they're very far away. And then also, of course, the lighting and the shadow. So just from the lighting on their clothes, the lighting on the buildings, you get the sense that there's a lot of depth going on there. This is why the one on the left doesn't really seem that realistic. Right? It's very clear that it's just a painting. Whereas the one on the right, it's fairly, it's not a photograph, but it's much more realistic in general. And you get the sense that there's a lot of depth there. So just a little bit more on that sort of geometric perspective. And it was noticed, well, maybe wasn't the first time it was noticed, but one of the first times it was put down into like kind of a rigorous formula or explanation was by this guy, Brunelleschi, where he sort of formally wrote down one-dimensional perspective. And that is essentially that if you have an object, like I said, an object that has parallel lines, so like a building, like the buildings in these pictures, the roof and the floor are actually parallel to each other in a well-constructed building. I mean, as long as they're designed to be that way. The roof and the floor are parallel, but if I'm standing here, I don't see them as being parallel because the objects are tending to get smaller as they get further away. So in fact, the roof and the ceiling are tending to look like they're going to get closer and closer together. Right? And if I if I kind of put lines on those from my perspective, they would actually meet at some point far off in the distance. And down at the bottom here, we see a drawing that utilizes that idea of one-dimensional or one-point perspective, where we have all these objects and they're all parallel. Technically, they're all sort of parallel in different ways. But from a perspective, if you're looking at these objects, you're going to see all those parallel lines wanting to eventually converge, or point at least to a point where they're going to converge. Right? So the road, even though it's parallel, off in the distance, it just comes together, it looks like one point. And the trees, even though they're all about the same size, if you want them to actually come off of a 2D picture, like they're all the same size, as they recede in the distance, they need to get smaller and smaller and smaller. So a lot of this has to do, well, it's very useful if you're going to do some art, you're going to do some drawing, you want it to be realistic at all, you want it to convey depth, then these sorts of things are very, very useful to understand. Okay, so then just kind of a fun example of perspective. Mainly, that geometric perspective still, where things that are further away are going to be smaller. Right? Even the same object, if you pushed it out further away, it's going to be smaller. It's going to take up less of your visual field. Right? That is true. That happens. But it turns out that if you look at a picture like this, you would probably say, your mind tells you, oh yeah, those are all gazelle, and all the gazelle are about the same size. Right? Look at the image, yeah, they're all about the same size. Right? It's a funny thing that our brain does because it's evolved to understand that image, that objects we will perceive them as smaller when they're further away. So if you see an object that, say, one version of it that's close, one version of it that's far away, and the far away one is much smaller, your brain was going to tell you that, no, yeah, that's just far away. That's about the same size. So, just to kind of play with you a little bit then, right, you have this gazelle all the way in the foreground, and another gazelle very far in the background, and again, your brain starts telling you, yeah, they're the same size, they're both gazelle, sure. But what happens if we just cut and paste that gazelle in the background and bring it to the foreground, right? So try to imagine for a second how big it's going to be next to that one in the foreground. Can you see it? Are you imagining it that small? It's quite small, right? It's almost bizarrely small. Even though you still look at the one in the background, and you look at the one in front, and you're like, yeah, wait, that one's regular size. Why is that so small? So this is part of our understanding of distance and depth, where our brain is telling us that the one in the background is still a gazelle, it's still part of the same group of objects, so it's still the same size. However, for that to be true and it to be far away, it's going to be, we're perceiving it as much smaller, it takes up less of our visual field. So if we do this weird thing where now we have pictures, we can cut and paste things, we cut it, paste it over here, it's kind of wild. We could do another example with the gazelle even in the middle of the frame, right? So this one's sort of in the middle. You think, ah, that one seems almost the same size, right? Again, almost the same size. Move it down here, wow. It's just weird. It's weird that our brain, this is how our brain has evolved to understand distance, and having this ability to just pull things from an image and move them around shows you a little bit of what your brain's doing with this information. I think finally, maybe we'll take the foreground one, or one of the foreground ones, and put it in the back and see what that looks like. Yeah, right, so take this one in the foreground, move it to the back, right? So before we do that, again, just try to imagine how the size of it's going to be relative to the other gazelle in that area. Right? Your brain is telling you they're the same size. But as far as how light works, the ones that are much further away are going to be much smaller. They're literally taking up less of your visual field. And now I get the monster gazelle in the background. Right? So now your brain's probably telling you that that is just an enormously large gazelle galloping in the back. Yeah, you can try this with your own images if you want to. Okay. So the last thing we're going to talk about in this lecture is getting now to the thing that does all this perceiving. So it turns out that the human eye is one of the most, as it says, one of the most remarkable instruments, optical instruments that we know of. It's amazing what it can do. You can see things that are close up clearly. You can see things that are very far clearly. You can change between them very quickly. You can see the spectrum of visible light, all the different ranges of visible light. You can see things moving at the side of your vision over here. You can perceive things in very low light. When there's a wide contrast between something that's very, very bright and something that's very, very dark, your brain can essentially cut off the ends of those a little bit so that you can still see everything in the picture, right? You think like HDR cameras are fancy, your eye is like well beyond that. It's crazy. So, how does that work? Right? So we're going to talk about lenses a little bit more in the next lecture, I think. But for now, just say that when a light ray travels, sometimes if it travels through a medium, it will sometimes bend. Okay? When it kind of slows down, it goes into a medium. And the whole front part of your eye, the cornea, the iris, the lens, all of that is essentially designed to bring in all the light that's hitting your eye and start to focus it back to the to the back of your eye, right? The inside of the back of your eye. Okay? So all of that sort of stuff is essentially a mechanism to focus light onto the retina, onto the very back of your eye. And it turns out that the retina, you have the retina covers the whole back of your eye, but it's much more refined, and you can see much better right in the sort of center area called the fovea. Again, I don't know how to pronounce that. Go with fovea. Okay. So on the retina are actually where the photoreceptors are. So there's cells that are designed that are essentially like little antennas. And so when the light hits them, they sort of, just like an antenna that picks up a radio signal, these antennas are picking up visible light signals. Say more about those in the next slide. But also, interestingly, after those light signals get absorbed by those photoreceptors, those signals need to be transferred to your brain, and they're transferred to your brain via this optical nerve. And it turns out that the optical nerve actually has an attachment at a point in our eye, and that point causes the blind spot. There's actually a point in your visual frame that you never really notice because you have two eyes for one thing, but there's a spot that if you close one eye, you can't actually see. I put a link down here. I'm not going to do it in the video, but there's a link to at least, you can just look up Google finding your blind spot, and it's pretty easy to find an example of a way to do it. Essentially, you look at a dot and an X, you close one eye, and you essentially focus on that dot, and you move the image in and out until the X disappears. And there you go, you just found your blind spot. So that's kind of fun to do. I'd recommend giving it a try. Okay, finally, so a little bit more about those photoreceptors, right? So those antennae that pick up the visible light, they're antenna for the visible part of the electromagnetic spectrum. And they're separated into two kinds of antenna, what we call the rods and the cones. And it turns out that the rods are particularly good for a low light situation, but they don't pick up color, basically. Right? So it's essentially like a black and white sort of image. And the cones are what handle color vision. So those would perceive different colors. And in this image, this is actually, I don't know what kind of microscopic image, but this is actually an image of these rods and cones. And if you look at it, the very long, sort of skinny things in this picture, those are rods, the more orangish, yellowish things in the image, versus the more red things in the image, they're kind of like this cone shape. So you literally, that's why they're called rods and cones, because they look like rods and cones. It turns out that the cones then that pick up color are sort of separated into three types of cones, essentially for low frequency visible light, meaning red, yellow, orangish, medium frequency, meaning sort of green, maybe some just kind of greenish, and high frequency, like blue and into violet a little bit. So there's those three different types of cones, and they're each picking up the three different wavelengths of light. And together with those kind of red, green, blue, you make up that you can get the essentially your brain can interpret the entire visual spectrum that way. Yeah. So that's it for the first lecture about light. As I said, there's going to be, I think, 2 more, basically just about light. And yeah, because it's very important and very interesting stuff, in my opinion. It also turns out that, like I said earlier, it was the study of light that really brought about an understanding of modern physics, being like not just quantum physics, but also understanding gravity better, special relativity, and general relativity. Yes. So that's it, and I hope you enjoyed that. Have a good night, and stay safe.